Let's talk more about vectors and how we add and subtract them. After today, you should be able to represent a three-dimensional vector in a Cartesian coordinate system, find how long it is, in other words, its magnitude, and the coordinate angles of that vector, and you should be able to add 3D vectors together. A lot of the items in the list we won't go through in this lecture because this is not in person. What applications do we have for three-dimensional vectors? When would you ever have a vector, in particular a force vector, that has three-dimensional components? Well, there are many. Here's a simple one. Any structure or machine that involves three-dimensional space will necessarily, well, not necessarily, I suppose, you could have a simplified two-dimensional problem, but very often three-dimensional representations of vectors are absolutely necessary. Here's a very simple example where the telephone pole is being supported and stabilized by a couple of wires going down to the ground, a couple of cables. And there's force in each cable, FA and FB, that helps to hold the pole steady. Now, if those were the only forces applied to the pole, notice it would just fall over because those two forces are not balanced out, right? They have components that don't completely cancel. But we're assuming there are other loads that are not shown. For example, maybe there are loads from the wires. You might have noticed on the corners of, street corners and other places, sometimes not only does the street turn a corner, but the wires turn a corner. And what you might notice is that there are support wires that are opposite to the way that the wires come into the pole, and a support wire in an opposite direction to the way that the wires leave. And of course, the reason for that is the wires themselves apply loads at the top, tending to try and pull the pole over. And so support is necessary in the opposite direction to prevent the pole from falling and therefore, hold up the wires and transmit electricity or data or whatever is needed, whatever the pole is there for. So there's plenty of applications that involve three-dimensional space. I took my daughter on a cruise a while back, and whenever the cruise ship would anchor at a port, I shouldn't say anchor, whenever it would tie off at a dock, they had multiple ropes, and it was really interesting to see them because, of course, the ropes were in three-dimensional space, right? They weren't just in two dimensions, but the ropes were made of other ropes that were braided together. It was interesting to see. They were huge because, of course, today's cruise ships are even bigger than the Titanic was. The Titanic is a small ship by today's cruise ship standards. In fact, I don't think there are any there are. I don't know if they call them micro cruises or what today, but they're becoming more popular. The problem with the smaller ships is that there's so much movement in the ocean and passengers can get seasick, whereas with a larger cruise ship, the net effect of the waves, hitting the ship is fairly small, unless, of course, you have very large waves. So these support wires are called guy wires, and they help hold the pole up against, wind loads or the wire, the weight of the wire. And how would we represent these, though? If we were trying to represent these vectors in x, y, z coordinates, how would we do that? Well, we do it the same way we would do our work in a two-dimensional coordinate system when we're trying to represent points and lines and so forth, because really the forces just act along a line. And so you might notice that relative to the base of the pole, where apparently the origin of the coordinate system is located, force A begins up at 4 meters in the z direction, whereas B begins up another 1.5 meters and therefore has a distance of 5.5 meters from the origin. Now, here's the interesting part. That's really not the reason that the vertical component, the z component of FA and FB would be 4 and 5.5 meters, well, it's not meters, I'll explain it in a bit, but it relatively be 4 and 5.5 respectively. That's not the reason. The reason is because from the base point to the end point of the line measures 4 meters in the z direction for FA and 5.5 meters for FB. Now let's be careful here because those are distances. Those are not actually forces. So really, since the force acts along the line, those dimensions in length only tell you something about the direction of the force. They don't tell you anything about the magnitude of the force. What's interesting here is that the geometry is very closely related to the force. So we can talk about position here, right, where the wire goes from A down to C, the other wire goes from B to D. The first wire from A to C carries FA, the second wire from B to D carries FB, or we would say perhaps applies force to the pole from the ground along BD. But what's interesting and very, very useful is the fact that the geometry helps us determine the direction of the force. So let's see how that's done. Well, we've got another example. So here's a radio tower that's pivoted at its base. Often radio towers, in fact, are, because they want to avoid moment loads at the bottom of the tower, but you don't know what that is yet. Most likely, I'll explain it later. But basically, think of the origin O as a ball and socket joint. So this tower, if it weren't for the wires, would simply just fall over under the slightest disturbance, wind or, maybe vibration from in the ground, whatever. It would just fall over. So the wires that go from D down to C to A and to B all carry force that helps stabilize the tower. But one thing we're particularly interested in is adding these forces together, because we'd like to know the total force at the top of the tower. You probably realize from intuition that the horizontal plane components, the XY components of these three vectors, must cancel out in order to not cause the tower to tip over simply from the force in the cables. But notice that the vertical component acting downward adds for these three vectors. And, maybe the cables are not in the right place. Maybe there is a component left over in the resultant, either in the X or Y direction, which would be bad. They need to all cancel. So how would we determine the sum of these vectors? In other words, the resultant, the net effect of these three forces? Well, we need the ability to add vectors together. And of course, these are three-dimensional vectors. But we have to back up a little bit, because while we know the magnitudes of the forces, all we really know for direction is geometry information. In other words, point C, for example, is 16 meters along the x-axis and 18 meters along the y-axis away from the origin. Of course, we need the height, and, I see it's given there, 24 meters. I missed it a moment ago. But we would need that information in order to represent the vectors themselves, the force vectors, and then add the vectors together to get the resultant. So these are two big things that we need, is representing force vectors in their proper direction and adding force vectors, of course, in three dimensions. All right. So generally, forgetting force vectors for just a second and studying the properties of vectors themselves. If we have some generic vector A, okay, and that vector obviously has some magnitude in some direction, we want to know just the direction part of it. We want to be able to separate that out, because remember, as I was showing you, we're going to have position vectors that indicate the geometry of, say, wires and things that carry force in the same direction as the wire. And we need to know a way to extract that direction information from a position vector. So how do we do that? Well, it's actually really easy. All you do is you take the vector itself, which has I, J, and K components, or X, Y, and Z components, and you divide it by the magnitude of the vector. That's what's being shown with the first equation. A unit vector in the direction of vector A, in other words, a vector that has length 1, not the length of the original vector, is equal to the original vector divided by the magnitude of that same vector. Now, this unit vector will have length 1, so it'll be a unit vector and has unit length. And so you can multiply it by anything you like in order to represent a different vector, such as force, that is in the same direction as the position vector. Also, the unit vector is dimensionless. It has no units. If you think about, let's say we're trying to represent force, but what we know is position. So we know a direction of a wire. When you take the vector itself that represents the position of the wire, the position information from tip to tail, and you divide it by its magnitude, what are you doing? Well, you're dividing something that has units of length by something that has units of length. Now, the thing in the numerator in this equation is a vector, whereas what's in the denominator is a scalar. But the units still cancel. So you'd have something, say, for A that has units of meters, for the vector, and then for the scalar, it also has units of meters. Now, it's a little bit confusing because I'm using the word units two different ways. When I say a unit vector, what I mean is that that vector has unity length. It has the number 1 for length, okay? That's how long it is. It's 1 unit long. But when I'm talking about the units of a vector, that's something different. I'm talking about what the vector represents physically. So far, we've encountered two different ones. We've encountered vectors that represent forces, but then there are also position vectors that represent lengths, and those are two different things. So when we divide a vector by its magnitude, its units, its feet or its meters cancel because it's feet over feet or meters over meters. But of course, the entire reason for doing this is to extract a vector from geometry that points in the direction that we know a force lies in. And so this unit vector will point in the same direction as the original vector A. Now, when we're talking about a Cartesian coordinate system in 3 dimensions, the unit vectors are I, j, and k, whereas the coordinate axes are x, y, and z. And you can see that I goes with x, j goes with y, and k goes with z. But the unit vector is not an axis, okay? The unit vector is simply a vector that has magnitude 1 unit that points along the respective coordinate axes. Let's think about how to represent a 3-dimensional vector in a Cartesian coordinate system. So we've got a vector A. We plot down an arbitrary coordinate system, usually aligned with something that makes sense to us as human beings. But this vector A needs to somehow be represented in this 3-dimensional space. And so if you think about bounding that vector by a box, the sides of the box would have lengths ax, ay, and az, and would actually represent the x, y, and z components, or the I, j, and k magnitudes of the vector. In other words, another way to look at vectors is think of it as walking along a path. So if you start at the origin, in this case, and you walk out ax distance along the x-axis, in other words, aligned with the I unit vector, and then you walk up by AZ height, you will be in the XZ plane. Please follow me here. You'll be in the XZ plane at the upper left corner of this box. Okay, and what you've done is you've moved up by AZ length along the x-axis, along the z-axis, in the direction of the K unit vector. The last thing to do is to move out in the same direction as the y-axis from that forward left-hand corner out to the tip of A, simply along the y-axis. And you'd move out a distance, AY. And you would then have moved from the base of vector A to the tip of vector A. It doesn't matter that you didn't move directly along the direction of vector A. What matters is that you went from the tail to the tip. And so the components of vector A then would be the magnitudes AX, AY, and AZ. And so to write down a representation of this 3-dimensional vector, we would simply write A as a vector. And of course, if I'm writing it on the board, I'll put a bar above it to indicate this is a vector because I can't make a bold letter on the board. But the vector A is equal to AX in the I direction, and then add to, in other words, continue walking, a y distance in the j direction, and then move a z in the k direction. Now you notice this order is a little different than what I showed you. This order, what would happen is you'd move out from the origin along the x-axis and then move in the xy plane over to the point beneath the tip of A, and then finally move up parallel to the z-axis to the tip of A. It doesn't really matter in what order you will move from the tail of the vector to the tip, and this is a valid representation of the vector A. In other words, vector A has some length along each of the coordinate axes, and AX, AY, AZ are those lengths. So if we project vector A onto the xy plane, that projection is called A prime in this case. You see it noted there. And we can find the magnitude of A prime by the same way you would a two-dimensional vector. Just use Pythagorean's theorem. Pretend it's a triangle, right? So use ax squared plus ay squared square root. By the way, if you're not familiar with this notation, raising a quantity to the half power is the same thing as taking the square root of that quantity. So A prime is simply the length of the triangle formed by AX and AY. And of course you can see that triangle shaded in gray at the base of the figure. Now we can obtain the magnitude of vector A by simply taking the length of A prime and the height of vector A and using Pythagorean's theorem once again. So the square root of the sum of the squares, which turns out mathematically to be the same thing as simply taking ax squared plus ay squared plus az squared and then square root of the whole thing. And so that's how you find the length of vector A, in other words, the magnitude of that position vector called A. This is not a force vector, this is a position vector. Now the direction of that vector can be represented by measuring the angles of the vector from the x, y, and z axes respectively with, and by the way, respectively means in the same order or in that order. So if I say x, y, and z and the coordinate angles are alpha, beta, and gamma respectively, what I mean is that the angle of vector A from the x-axis is alpha, the angle of vector A from the y-axis is beta, and the angle of vector A from the z-axis is gamma. If you're not familiar with Greek letters, they are in that proper order. The text reads, A is defined by the angles alpha, comma, beta, comma, and gamma, period. So those are symbols alpha, beta, gamma. And it's kind of like using ABC, except Greek letters. Why not use ABC? Well, we often use our usual language to represent vectors, and it would be confusing if we used, some other letter from our usual alphabet to indicate the angle. So we simply use Greek letters instead. Now, an interesting thing about these angles is that they can only vary from 0 to 180 degrees. If the angle between, say, the vector and the x-axis is 0, that means that that vector lies along the x-axis necessarily. It has to. And therefore, beta and gamma would be 90 degrees, wouldn't they? Because then the angle between the z-axis and the z-axis and the x-axis is 90 degrees. The angle between the y-axis and the x-axis is also 90 degrees. But the angle between the vector and the x-axis can vary from 0 all the way to 180 degrees. And so the vector A could point in the opposite direction to the positive x-axis, and therefore alpha, and it turns out the same argument holds for beta and gamma, varies between 0 and 180 degrees. Now, the so-called direction cosines from trigonometry is cosine of alpha equals the length of A along the x-axis, called AX, divided by the magnitude of vector A. These are equations that are useful for helping you find the coordinate angles, alpha, beta, and gamma. Most of the time what you would do is you would know the distance AX, in other words, the magnitude of vector A along the x-axis, as well as the total magnitude of A, divide one by the other, take the inverse cosine of that ratio, and that would yield alpha. And so all you're doing is solving these three equations for the angles, the coordinate angles. Now, one thing that's you need to make sure you can do, you need to make sure you can take an inverse cosine on your calculator. So you need to get your calculator out now and figure out how to take an inverse cosine. And be really careful, because you want to know whether your calculator is set in radians or degrees. Because when you take the inverse cosine, it's going to return an angle, but that angle might be in degrees or it might be in radians. So make sure you know how your calculator is set and you're able to change it if necessary. Now, the angles, alpha, beta, and gamma, are not independent. It turns out that the square of the cosine of the angles, or the square of the, how should I say it, the sum of the square of the angles has to be 1. And of course, you can verify this, or at least not really verify, but you can see an example of that by imagining vector A as lying along either the x, y, or z axes, and you'll realize that the other angles are 90 degrees, and cosine of 90 degrees is, 100, no, I'm sorry, cosine of 0 is 1, whereas cosine of 90 degrees is 0. And so what you would end up with, let's say that vector A lies along the x-axis, what you'd end up with in the first term is 1 squared, right? Because cosine of 0 is 1, because 1 squared is still 1. But then beta and gamma, both being 90 degrees, their cosines would be 0, 0 squared is still 0, and we end up with 1. So that's an example of how this equation works, but it turns out that it always works with any arbitrary vector. The angles are not independent and must follow that equation. Now, one way to realize this fact is to think about a unit vector. So let's take not any arbitrary vector A, but let's take a unit vector that we know has length 1. Now, that unit vector could be derived by, if it's related to A, by taking the vector A and dividing it by its own magnitude, A, right? And so each of the coordinate, or the components of the unit vector would simply be the component of vector A divided by the magnitude of A. So along the x-axis, we'd have AX over A. Along the y-axis, AY over A. And along the z-axis, AZ over A. And another way to write this would be to say, well, if we need the length of the unit vector that points in the same direction as A but has only magnitude 1, we could write it by taking the cosine of alpha, that would actually be the x component of that unit vector in the I direction, plus cosine of beta in the j direction, plus cosine of gamma in the k direction. And we already know that the unit vector has length 1, and so to calculate the magnitude of the unit vector UA, all we need to do is square the components of that vector. So cosine squared of alpha plus cosine squared of beta plus cosine squared of gamma. Add them together, we better get 1 because that's the way you calculate the length of a vector, and we know that the unit vector has length 1. Now, adding these three-dimensional vectors together is very simple. Once we get the Cartesian form of the vector, all we have to do is add their individual directional components, and we can add vectors together. So if we want to sum forces, for example, if we want to take several different forces applied to a body and add them together, all we have to do is add the components of each of the individual forces in the consistent direction. So all the I components get added together and result in a component of the resultant vector in the I direction. Same way with the Y and the Z direction. So, for example, if we have two vectors, A and B, and each have components AX, AY, AZ, BX, BY, BZ, then to add them, we simply take the components that share the same direction, for example, the I component, and add those two components together, and the result still points in the I direction. Same thing with the J and the K. And so we end up with a resultant vector, a sum of two vectors, that is simply adding the components of the vectors together. Now we can subtract vectors as well. If you attach a negative sign to a vector, what you're really doing is taking the opposite direction vector from the original one, and then we simply add those together in order to subtract. So that negative sign, really what it does is it takes B and reverses its direction, and then we simply add vectors A and the negative of B together, and you see how it comes out here. So it's very simple once you try it. It probably seems a little more complicated to you right now than it really is. Now, some important notes for you to consider is that sometimes 3D vectors are given as a length and the coordinate direction angles, in other words, alpha, beta, gamma, or magnitude and projection angles. And so you'll see examples where I use both of these forms and understand how to work with them. But you should be able to use both of these in order to change the representation of the vector into Cartesian form. Really, Cartesian form is the king. It's the thing that we really want for our vectors in order to work with them. So, for example, we've got a force that has components in the x, y, and z direction, and you should be able to calculate the magnitude of this vector easily. Just take 10 squared plus 20 squared plus 30 squared, take the square root, and that would be the magnitude, the total force of the vector, still in newtons. However, the components of the vector, of course, are as shown here.